Hi there, you are watching a video of shell and tube heat exchangers for industrial plants. In a shell and tube heat exchanger, two fluids circulating at different temperature conditions exchange heat through the walls of the tubes, without direct contact between the fluids. In order to understand the configuration of this type of equipment, it is necessary to bear in mind that there are two different fluids circulating inside the exchanger without mixing. For this reason, the equipment is divided in two circuits, tube side and shell side. Therefore, to understand the arrangement of shell and tube heat exchangers, it is essential to study the bundle arrangement and the shell configuration. The tube bundle is an assembly formed mainly by the transfer tubes and the tube sheet, inside the shell, coinciding the center line of both elements. The main parts of this element are stationary and floating tube sheets, transfer tubes, tie rods and spacers, and transverse baffles. Tie rods and spacers keep all the elements of the bundle as one piece. The function of tie rods and spacers is to create a rigid structure between the tube sheet, the baffles, and the tubes, constituting the tube bundle as a single item. For removable tube bundles, one end of the tie rod is anchored to the fixed or stationary tube sheet. The required number of tie rods and their size is a function of the shell diameter and should be distributed evenly throughout the outside edge of the tube sheet. Tube sheets are generally flat circular plates, drilled with circular holes where transfer tubes are inserted. The purpose of the tube sheet is threefold. First, it divides the flow between the shell and tube side, preventing direct contact between the fluids. Secondly, it constitutes the most important structural element, withstanding the shell and tube side pressures. And third, it supports all tubes of the bundle. The tube-to-tube sheet joint must warranty a tight seal preventing the process fluids from mixing. Therefore, this joint is critical to the operation of shell and tube heat exchangers. The tube sheet design must account for the following elements: threaded holes for lifting devices, tube holes, threaded holes for pulling devices, grooves for channel side pass partitions, and threaded holes for tie rods. There are basically three types of tube sheets. Fixed, they are welded to the shell or to the stationary head. Stationary, these tube sheets are embraced by the shell and the stationary head. And floating tube sheets, they allow the free displacement of the tube bundle. Stationary tube sheets are normally used for removable tube bundles. Floating tube sheets are embedded in floating heads, designed to allow the free expansion and contraction of the tube bundle. Tube sheets are a key element in heat exchangers. For that reason, the design and calculation must be carried out taking into consideration all factors that can increase the thickness, such as slots, corrosion, grooves, coatings, etc. Tube sheets can be designed and calculated according to the TEMA and ASME codes. Depending on the client and project requirements, one of these two design codes is applied. The TEMA code design and calculation procedure will be described. Tube sheets are designed for the most critical condition, due to the complex load system acting within the heat exchanger, shear and bending stresses are present in all types of tube sheets. The required thickness due to bending is a function of the union factor, the gasket mean diameter, the effective design pressure, the allowable stress of the material at design temperature, and to the coefficient due to the number of passes. Similarly, the required thickness due to shear stress is a function of the equivalent diameter, the external diameter of the tubes, the arrangement pitch, the design pressure, and the maximum allowable stress of the material at design temperature. Once the results of both shear and bending calculations are obtained, they are compared and the greater thickness is adopted. Material selection for tube sheets must also be addressed with special care due to the potential corrosive attack at operation conditions of both fluids, and particularly for the most critical one. This element can be fabricated out of plates or out of forgings. While plate fabricated are less expensive and normally deliver in thicker designs, forged ones generally have higher level stresses, requiring longer lead times though. The function of transverse baffles is to support the tubes and direct the flow in the shell side. From the standpoint of the fluid that circulates through the shell side, baffles have a segmental cut which may adopt various configurations, being the most used configurations vertical and horizontal cuts. The baffle cut percentage is specified in the datasheet of the heat exchanger. In most cases, mainly due to fabrication restrictions, the exact percentage cut cannot be applied. It is located on the center line of the row or column of the tubes closest to the specified percentage, or in the gap between them. When the number of passes in the shell side is greater than 1, it is necessary to install a longitudinal baffle to divide the flow. All baffle configurations seen so far correspond to one shell pass. In other words, the fluid travels all the length of the shell only once. In some cases, sensible thermal gradients between the two fluids, for instance, it is required that the fluid travels the length of the shell more than once. Longitudinal baffles are used in these cases, as shown in the picture. Normally, when longitudinal baffles are installed in shell and tube heat exchangers, it is required to use sealant strips. The function of these sealant strips is to prevent leakage and maximize thermal transfer. In other words, seal plates prevent the flow from crossing from one pass to the other through the free spaces between the longitudinal baffle and the inner wall of the shell. In this section, we will cover the design and calculation of heat transfer tubes, cylindrical elements similar to a pipe. The design of transfer tubes is critical to the exchanger's efficiency. This is due to the fact that the fluids interchanging heat circulate at both sides of the tube, internally and externally. Commercial tubes used for heat exchangers are different from pipes used for fluids transportation. The tubes used in the fabrication of shell and tube heat exchangers is calibrated. It is specified according to its outer diameter, that coincides with the nominal diameter, and the wall thickness. The wall thickness, or gauge, is determined according to the BWG scale from 1 to 31, where each number corresponds to a specific thickness. The correspondence between the BWG number and associated thickness can be found in several publications. For example, caliber BWG14 corresponds to 2.108 mm, while caliber BWG16 corresponds to 1.651 mm. As mentioned before, the design and calculation of transfer tubes is critical for the efficiency of the exchanger. The first step is to define the design code to be used for the tube's thickness calculation. This is indicated in the design code of the heat exchanger. Both the TEMA and HEI codes require that the ASME code for pressure vessels must be followed for the calculation of parts under pressure. For most applications, the tube wall thickness is obtained using the equations of the ASME code, section 8, division 1, for cylindrical shells, as shown in the picture. The required thickness is a function of the inner radius, the design pressure, the joint efficiency, and the maximum allowable stress of the material at design temperature. At the same time, and independently from the thickness required due to the calculation, transfer tubes shall meet the minimum thickness requirement included in the design code. Since the tube sheets and tubes are dividing elements between the two fluid streams flowing through the heat exchanger, these elements must be robustly joined to prevent leakage. For most shell and tube heat exchangers, tubes can be attached to the tube sheet by different means. These are using mechanical expansion or hydraulic expansion, by welding, and to a lesser extent by fusion of the elements through controlled explosions. For most applications, preferred solutions are expansion, either mechanical or hydraulic, and expansion plus welding. The impingement plate is a device that is installed in the shell inlet nozzle, perpendicular to the direction of the flow. The aim of this plate is to prevent the fluid stream impact directly on the tubes of the bundle, damaging the tubes due to erosive effects. Impingement plates can adopt different configurations: flat plates, perforated, curved plates, wear tubes, etc. The selection of one of these methods will depend on the speed of the fluid, corrosivity, and the desired fluid distribution. For cleaning and maintenance operations of shell and tube heat exchangers with removable tube bundles, devices and accessories to facilitate the extraction of the bundle are needed. For removable bundles, the tube sheet must be designed including threaded holes for pulling devices. These holes must be covered during normal operation to avoid fluid sedimentation, possibly damaging the thread.